everybody. Today we'll do another video, and today we will do another videos in mathematics. And in I don't know if I have in this. I don't remember if I have any videos on differential equations in this channel, but if I don't have any, this is going to be the first one. So I will probably do some differential equation problems, and I am using the book right now. I am using the book it's called the first course in differential equations, and it's pretty good actually. I guess not the best, but it's pretty good. But it still has some bunch of pictures in there, like galaxies and stuff like that. I guess people want to, try to show that differential equations, play a role in discovering the, the space, But I will say, good luck with that, of finding everything what is there. So that's what I can say, and also I will find some areas. I will study the area today. Let's do an example of which is called exact. This marker was working. It will be much better. Exact differential equations. So I will give it a little definition of the differential equation, of what is an exact differential equation. Nowadays definitions, I guess they don't matter anyway. And again, this is conservative engineering academy. So this is like I am not a liberal, so I guess you can actually take by the name of the channel, right? I am not a liberal. But the bottom line is that they try to define the words, right? They try to give a different meaning. Like a woman, they don't want to call it a woman anymore. They want to call it women in plural. They want to call it birthing people. I guess the definition of the differential equation, what is an exact differential equation? I guess it's not so much, right? I guess nowadays, because we have the new era of the people that want to try to be smart, redefining things, and they want to, kind of be smart. But I want to define a little bit what is an exact differential equation. What an exact differential equation is that has to be exact when, like, let's say, for example, in the case of you have M, and we know that M, right? So, we don't know what M is. I think I didn't define that yet. But technically, M is a function. So M is a function of x and y, right? And also, that is differentiated at dx. And then we have a plus n, right? So n with a function of x and y again, but this is differentiated at dy, which is equal to 0, right? So if this function is differentiated, x and y, we know that differential equations is basically, in general, differential equation is a function that includes derivatives, right? And an equation that includes derivatives, and we're trying to go back and find the original function and how the original function of that derivative was, how that rate of change help us to kind of go back and try to find the set of solutions that satisfy that differential equations, right? Using the original function, I will say, right? So by doing that, so we have a combination of of m, and with combination of n, the derivatives over here, right? So dy and dx, right? And that is equal to something on this side. That something might change eventually. That was, in this case, they set it up as to 0, which is technically right now, we're not saying that this is a homogeneous differential equation, right? So we just say that it's an equation that involves the derivative with m and m as a function on x and y dx plus an n was a function on x and y dy equal to 0. Now, by doing this, we will have to redefine this again. I have to kind of say that redefine things, right? Which a man is a man, right? But in a woman is a woman. Like, men cannot have kids, right? They cannot give birth. I guess a pretty good definition. But in this case, we have to redefine this. We say that the partial derivative, I would say, did I say redefined? No, it is already defined. We're not redefining anything. We just define. I am just stating what the book says. So what it says is the partial, if I had a marker that works, would be very helpful. The partial derivative let me see. Maybe this works. The partial derivative, right? The partial derivative of m with respect, right? The partial derivative with respect to the partial derivative of m with respect to the partial derivative of y equal to the partial derivative of n with respect to x, right? So now, if I take this, right, and I can say, okay, so the partial derivative with this, so then it's equal to the partial derivative with respect to x, it belongs to this, and this to that, right? Right. I guess, like cross multiplying, I guess. But this is what happened when this has to somehow be equal, right? So if we can identify that this partial derivative, when we take the partial derivative, are indeed equal to one of the function, and the function in the left is somehow related to the function on the right, then we say that its equation is exact, right? So, with that being said, let's get started, right? So basically, we can actually say that we can also say that we can also say that m x comma y dx plus dx, right, plus n x comma y dy equal to the partial equal to, and I'm going to write it here because I don't have a lot of space, is equal to the partial m over partial x dx plus partial n over partial y dy. And you can see that the partial derivative and the regular derivatives are here, because what I'm saying is I'm taking the partial of this, right? And this is still here, right? So this little thing right here is still playing this regular derivative, right? I am just taking the partial derivative of one of the functions, whatever I want to do, what I would do, partial derivative with respect to x or with respect to y. Now, so with that being said, let's do an example real quick. So let's get this done. So, and you will be surprised how much work we will do and what the answer will be, which is, at the end of the day, it's going to be kind of one of those things. So, okay, so let's do this. Hopefully, we do this a little quick because this, again, is a little time consuming. So, we will just knock this out kind of quick. So let's say, for example, that we want to solve this, right? So we want to solve, let me just give myself a little space here. Okay, so let's say that we want to solve it says solve, right? So it says that the expression is as follows: is 2xy 2 and this is number 2. So 2xy, right? And the derivative for that is in the form of dx, right? And then and the next one is x squared minus 1, right? X squared minus 1 dy, right? Dy, right? And that, indeed, they say and that is equal to 0, right? So, with that being said, we can actually start doing some work over here already, right? We can start comparing this and identifying whether these are exact. Okay, so in the first, let's take the derivative of one of them, right? A partial derivative with respect to something, right? So if I take the partial derivative, right, with respect to y in this case, right, and I compare it, right? If I take partial f, right, the partial derivative of this, right, of the function of this function with respect to y. Oh, I can say m. I can say m instead. Technically, yeah. So m, right? So if I do that, right, partial m, with respect to y. And I keep my x constant. So what it does, I'm taking the derivative of this piece right here, which is this is m, and this is n, right? So if I take the partial derivative here with respect to m, and I'm keeping my x2x constant, then that means that I have 2x, isn't it? Isn't it? Right. So with that being said, we compare, right? We compare. And we said, okay, so if I take the derivative, right? If I take the derivative of this function with respect to y, right? What do I get? Well, I get this, right? I just take the derivative of that with respect to that, right? So what I'm getting is 2x, which is, if I take the derivative of with respect to x over here, I'm going to get 2x, isn't it? Now, it's a good thing to point out too. It's a good, I would say learning, method. That also we can say that the partial derivative of 2x and the partial derivative, if I take the partial derivative of this, right? Now, look at this. Let's say that a y wasn't here, right? If a y is involved in this equation, if I take the partial derivative, right, with respect to y, now, look, I don't know if you can see this, but let's say that if a partial derivative, if a y was here, if I take the derivative with respect to y, I will get exactly what is in here. See that? They are related, right? They are totally related. So we also can say that the partial f and then partial y, right? Partial f, partial x is equal to 2xy, right? And partial f, partial y, partial f, partial y is equal to x squared minus 1. Now, okay, so we just prove it by taking the derivative with respect to y, we get that, and we take the derivative with respect to x, we get this, right? Take the derivative right here, partial f, right? Partial. So you take the derivative of partial f, right? Partial x in this case, I get 2x, isn't it? So these are equal, right? So derivative with respect to y, keep x constant, I got this. Take the derivative with respect to x, right? Over here I don't have a y, so take the derivative with respect to x, I get 2x. So this is the relationship. Now, if we erase this and do the rest, so we prove that these are exact. The m and the x are exact. Now, we can take the partial derivative with respect to, from the equation, we can actually say that we can take the partial derivative of, we can integrate, right? We integrate m, right? So if we integrate m, what do I get? If I integrate m with respect, if I integrate m, right, keeping y with respect to x, keeping the y constant, right? So what do I get? So if I integrate m, right? So integrate m, so I take the integral of 2x y dx, right? But this is m. If I integrate that, I get what? I get 2x squared. I am integrating with respect to x. Remember, keeping the y constant. And also, keep in mind that instead of getting a c as a constant, we will get y. Right? We will add another function g of y. So just keep that in mind. So g of y is going to be the constant for this. So, okay, so but I have a y, right? So I have a y, and I give the y, right? And plus g y. Plus gy. Now I am not done here because I should divide by what? I should divide by 2, right? That's how we integrate. So we cancel this, right? And then we get what? We get x. We get x squared y plus g of y, right? That will be the integral of that. Now, if you look at this is a z. When you actually doing regular integration and indefinite integration, you will get this, right? You will get a plus c, but in this case, we got a plus g of y. It's another function, right? It's another function. I will say, if you're looking at this, another family of functions, right? Because that was differential equation. It's another family of functions related to this. Yeah. So, okay. So now, let's get the rest of it. Okay, so if we do that, then we integrate, right? And then we set this into we set this piece to m because we already proved that the m is equal to n. Then we can actually try to make this equal. Okay, so let's do that then, right? Let's do that. Okay, so now what we can do here, right? So what we can do here is, let me just erase this. If this, so, okay, let me just keep the 0 in there. Okay, so now we have, we integrate m, right? Now we will go back and take the derivative of m, right? So if we take the derivative of m with respect to y, so now we integrated taking the integral with respect to x, right? Now we'll take the derivative of m with respect to y. So we can do is, okay, we can say df partial, right? Partial with respect to y of x, y plus g of y. Now, if you see this, if I take the partial with respect to y, I get x squared x squared plus, so now x is a constant, and then x is a constant, and then I get prime, I get g prime of y, right? Okay, so now I got a constant, another constant, and now that constant is being a derivative. Look at that. Now, with that being said, so now that I have this, I can actually say that I can set up equal to n, right? So n initially with this, right? So n was initially that. So what I can do is I can set up this equal to this, right? So I can actually say that x squared plus g prime of y is equal to x squared minus 1. Look at this. Now we're doing algebra, isn't it? Do we see we're not taking derivatives or doing integrals? Well, we'll do one more integral. But right here we're doing algebra. See? So right here I subtract x squared on both sides, right? So if I subtract x squared on both sides, this go away, right? And I get a g prime of y equal to negative 1. Interesting, isn't it? Now look at that. So now I have that. So g prime of y so g prime of y equal negative 1. Right. But what is g prime? G prime is saying I dy dx again, right? So that means that I have a derivative. This little g prime is a derivative, which means that I have to take the integral again, right? So, and I take the integral of this, right? So when I take the integral of this, I get y is equal to, I'm taking the derivative with respect to y. So in this case, but I'm with respect to y, but I want to get g, right? So that means that g now is nothing but negative, I will say, so if I integrate that, g of y now is equal to negative y. So now I took the derivative, I integrate with respect to y again, and I got that g of y is equal to negative y. Interesting. Okay, so look at this. You got a negative 1 over there, you got a negative y. Now, the question will be, can we say that the solution is done already? Can we say that the solution is this? F of x comma y, right? Because actually, in this case, I replace the g, right? So when I took the partial, when I integrated, right? I integrated and with respect to with respect to y, and I got, no, with respect to x. So when I integrate with respect to x, I got f of x comma y, and it's equal to x squared y plus g y, isn't it? Now, can I say that this is equal to this is equal to this, and this is equal to that? It is a valid statement, actually. I can actually say that if I replace this, right? If I replace that g, the g of y, if I replace the g of y, right? I can say that if I replace this g of y by the negative y, I get x squared y minus y, isn't it? Okay, but that is a very interesting case because it is about a statement, but remember that the whole idea of getting that the implicit form is, right? So the implicit form of this should be equal to a constant. And the question, why, right? Why was equal to a constant? Because we integrated here. We integrated this one. So if we integrate this and we end up with a simple number like that, that means that we should say that we could say that the whole thing turns into a constant and can be written as this. Can be written as xy minus y, x squared minus y is equal to a constant c. Okay. So look at this. Now, if you look at this, you could actually factor out, right? You factor out a y. You factor out a y, add it there, and you get x squared minus 1 is equal to a c, right? Now, you take this, and you said, okay, so you can say that y, you divide by this, right? You divide by x minus 1, and you get that z over x squared minus 1. It's another valid statement. But the bottom line is that none either of those are valid solutions. And the reason why is because a constant integration of g. See? That's the point that I was trying to make it, that because, now write it again, not redefining, but defining what is stated for the mathematicians, right? I guess the same thing as just stating what God said, male and female. Okay. So it's stated like God created male and female. It's kind of odd if I try to redefine things, right? So it's stated pretty good definition of male, right? And the females, It's totally different. Um, you can identify it. If you cannot identify between how the male look like and how the female look like, I don't know what world you're living in. But in this case, because we define what the mathematician says, right? Because B because so B because the integration of a constant G prime, constant G prime, right? So let me just constant G prime of Y, right? Because it was a constant. That means that the whole thing, because the integration of this was a constant, if this was not a constant, then we will have a different solution. But in the case, because it was a constant, just a pure constant, we just got a pure Y out of it. That means that we have the solution is simply f x comma y is equal to z. Okay, so we went through that much work. If I was a student and just why should we be doing this, the whole thing, right? All the work. If I knew this, was that the answer? Mathematically, this kind of makes sense, right? That also kind of makes sense. But the real solution, the true solution, because we integrated this y, and that came out when we integrated as a constant number, that means that we actually set it this way. So in other words, it's just a constant. The whole thing is just a constant. So yeah. So that is the solution for this problem. And if you find it interesting, just give me a like. And I see you in the next video. Thank you for watching.